Aloha! This is Lynn Turbeck again, and this is the final installment in our screencast covering CS111 Lecture 5 slides on Booleans and Conditionals. When we last left our heroes, that's you were defining two functions that use conditional statements, add article and sum unique. Let's talk about some solutions to these functions. Here's a solution for add article. So add article here is taking a string s, and it's going to begin with a conditional test on the length of the string, because we want to specially handle the case where the string is empty. So here we're going to have this outer conditional statement that's going to test the length of the string. If the length is greater than 0, we're going to go off and do some more tests. Otherwise, we're simply going to return the string unchanged. That's one way to deal with the empty string. So in the case where the length is non-empty, notice we have a nesting of conditionals in the then branch of the conditional. And we're going to do a test to see if the first character of the string is a vowel. And if the first character string is a vowel, we are going to concatenate the string and followed by a space to s and return that. Otherwise, we're going to concatenate the string a followed by a space to our string and return that. One more thing to note is that many people are tempted in a situation like this to test if the result of is vowel of s sub 0 is equal to true. I see this a lot in the code of students who are new to writing if statements, and that's completely unnecessary. Look, this is vowel here is a Boolean expression. It's something that already denotes true or false. So if it's true, if you write this extra stuff here, you're saying testing if true is equal to true, which is of course true. And if it's false, you're testing if false is equal to true, which is of course false. So this doesn't add anything. Please never write this. It's just awkward. This Boolean expression here is all you need. You never need to test if a Boolean expression is equal to true or equal to false. So just don't do that. Okay, how about a solution for sum unique? We're going to look at two. Here's our first approach. In our first approach, we have in the body of sum unique 5 different statements. There's our first, which is an assignment, followed by 3 elseless conditional statements, and then our 5th statement is return. In our first statement, we are going to allocate a local variable named sum that initially contains 0. And then our subsequent if statements are going to potentially add to the current value of sum one of the values x, y, or z, depending on whether they're unique. And at the end, we will have added and changed sum to be the sum of all the unique numbers. And so at the very end, we're going to return that. So how do we determine if a number is unique? Well, for instance, let's take a look at x. To determine if x is unique, we make sure that x is not equal to y and x is not equal to z. If that's true, then x is unique. And what are we going to do? We're going to change sum to be whatever the value of sum plus x is. And so we would change sum now to be x. If we determine that y is unique, we're going to change whatever the current value of sum is to be sum plus y. And if z is unique, we are going to change the value to contain sum plus z. Notice that here the notation sum plus gets z is shorthand for sum gets sum plus z. So it's just a shorter way to write the same thing. That's one solution strategy. Here's a second solution strategy. In this strategy, we have a single conditional statement. That's a chain conditional that has 3 elifs and an else. Let's see how this one works. Okay, in our first test, we test if x is equal to y and y is equal to z. Well, if that's true, x, y, and z must all be the same number, in which case none of them is unique, and we can immediately return a 0. Let's say we now make it to our second elif. In order to make it to the second elif, it must be that the first test here was false. So it can't be the case if we make it to the second elif, that x, y, and z are all the same, so at least one must be different. So now suppose we determine that x and y are the same. So if x and y are the same, then x and y are not unique, but z is necessarily unique because we couldn't have gotten to the spot with at least one unique number, so we can just immediately return z. So we do similar tests at this point. If we discover that x and y are different, but that x is equal to z, then certainly x is not unique. But now we know that y is unique because, again, we couldn't have reached this point without at least one value being unique. And if we determine that y is equal to z, then neither y or z is unique. But again, we could only come to this point if at least one of our values is unique, so we return x. If all of these tests fail, it must be the case that x, y, and z are in fact all unique. And in that case, we return x plus y plus z. Before we talk about anything else, I'm now going to channel Stephen Colbert on the notions of truthiness and falsiness in Python. So it turns out that what happens if you use a value that's not true or false in the test position of a conditional. Is it an error? Well, in many languages it is, but in Python it is not. So it turns out that in Python, you can use any value in the language in the context of a conditional or an and or an or, and it is not an error. And if that's not confusing enough, it turns out that in these contexts, certain values act as false and other values act as true. In particular, in the context of a conditional statement, we have the case that a small number of values, including 0, the empty string, none, the empty list, the empty tuple, and the empty dictionary, all of those values act as if they're false. So they take the false branch. We call these falsy values. And anything that's not a falsy value is called a truthy value. So consider the following test. So here we define something called test truthy, and all it does is it takes in a value and it puts value in the test position of an if statement. And if the then arm is taken, it returns truthy because it's a truthy value. And if the else arm is taken, it returns falsy because it's a falsy value. So let's see. If we go through our examples here, well, certainly we expect that true should be a truthy value and false should be a falsy value. But 17, as an integer, it turns out is not 0, and any non-zero number acts as true in the context of an if, so that's truthy. But 0 is special, and in the context of an if, it counts as a falsy value because it will take the else branch. Similarly, any non-empty string is truthy, like hello, but the empty string is falsy. The none value is also falsy. A non-empty list is truthy, but a empty list is falsy. This is all very confusing. And we in CS111 think it's incredibly bad style to write a test such as this that has a test expression that is not a Boolean value. And we strongly, strongly recommend that you always write your conditional tests so that they are written in the context of being a Boolean expression as opposed to being some arbitrary expression that's non-Boolean. And then you won't have to worry about this whole truthy, falsy business. It's also, while we're talking about this topic, let's talk about what these values do in the context of or and and. And this is also quite confusing, but you might see it in practice, so you should know what it does. If you have a or that begins with a falsy value, such as 0, it turns out that it always returns the other result. It returns the result of the right operand. So if the left operand is falsy, it necessarily returns the right operand. So if the right operand is false, it returns that, but if it's truthy, it returns that. So in fact, what we get here is it returns a 4. If the first value of an or is truthy, that gets returned immediately. So we don't even evaluate this expression here, and we just return the first truthy value. With an and, what happens there? Well, in an and, if the first value is falsy, we know that the whole result must be falsy, and we just return whatever that falsy value is. But if both values are truthy, we return the second truthy value, which in this case happens to be 9. And the same thing is true of strings. So now if we take a look at string example, since the empty string is falsy, this OR will return the A, which is the truthy. Since this OR begins with a truthy B, that's what gets returned. In this AND, it starts with a falsy, so that falsy gets returned. But this AND has two truthies, and the second of the two truthies gets returned. Again, very confusing, and this is not something that is for the squeamish to be used in this fashion. Now we're in a position to explain exactly what the isVowel4 function from before did. So remember, we now have the example where we were combining the letters A, E, I, O, or U by the OR logical operator. But now we know, because A is truthy, that in fact that whole thing simplifies to A. So in fact, all isVowel4 was doing was testing if the lowercase version of S was the letter A, and it wasn't paying any attention to the E, I, O, or U, and that's why it didn't work. Okay, our goal now is we're heading off to try and define a high-low game, but before I can do that, there's one more detail that we have to understand. And that detail involves the notion of state. So let's just review the idea of state. So what state is in a computer program is just the set of values that characterize the process at a particular point in time. So for instance, if we define an ellipse, it's the case that that this ellipse is characterized by the major and minor axis. So this is something that's an ellipse that fits into a rectangle that's 100 units wide by 30 units wide. So those are two pieces of state. And additionally, if we set the fill color to red, then the color changes from whatever default color it is to red. And if we change the fill color to yellow, it has the same state as before in terms of the width and height, but now it's the case that the fill color is yellow. So all these are examples of changes in state. Now let's talk about the notion of local versus global scope in the context of some concrete examples. So take a look at this example here and see if you can predict what's going to happen. What do we have? We have an example in which we define a variable x1 that's initialized to 5. We print out its value. We then define a function f1 that sets x1 to 7 and prints out x1. Then we invoke f1 on 0 arguments and print x1. And the question is, what sequence of values do we see printed out? Well, it turns out you have to understand in detail what's going on with the model of variables here. So when we define x1 to be 5 here, x1 gets 5, we are creating a variable, which is just a name box, and we are filling it with the value 5. Now it turns out, when we define a function, that if we assign to any variables within that function, by default, those variables are different than any variables we have defined outside. So it turns out that inside of f1 here, we have a completely different variable named x1 that is 7. And it is not the same as this outer one. So this outer variable is called a global variable. And this inner variable is called a local variable, since it's local to f1. So what happens here? This print over here is printing the value of the global variable, which is 5. This print over here is printing the value of the local variable, which is 7. And when we're done executing f1, all of the local storage goes away. And in fact, when we refer to this x1 here, we're referring to this x1 over here. We're referring to the global one. So in fact, since the inner one has gone away, we are referring to the global one. And the global one has an unchanged value, which is still 5. So the result, maybe somewhat surprisingly printed out by this program, is 575. Now, what if we wanted it to be the case that we wanted to say that when we are changing the value of x1 here, we want it to be this value of x1 and not a value of x1 within f that's a new value. How can we say that? It turns out that this is possible. So the way you do that is you have a special declaration called global. So here's another version of the example where we've changed all the numbers from 1 to 2. So we have a variable named x2 and a function named f2. And it's the same as before, except that now we have this new declaration that says global x2. And what that means is because I have declared global x2 within the function f2, it means that if I assign to x2 within that function, I am referring to the very same x2 that I defined outside the function. That is the global one. So in this case, what we have is we initially have defined a variable x2, that is 5. And then when we invoke the f2 function here, it goes off and changes that existing variable to have the value 7. And so what gets printed out here? Well, in our first print, we print out the original value of x2, which is 5. Then in our second print, we have changed that value from 5 to 7. And in our final print, since there was only one value of x2 in this case, the final value is 7. So this is a different behavior than before, because before we hadn't changed the outer value of 5 to 7. But in this case, there was only one x2, and we have in fact changed that. Okay, let's just consider two other examples while we're here. Suppose we never defined the outer variable initially. So here's another version where, again, we have changed the x value to x3, the f value to f3, and we right away declare that x3 is global. So since we declare that x3 is global, when we assign the value 7 to x3, that value is being assigned to a global version of x3. So this is now the global version of x3. It is not local at all to f3, so that when f3 goes away, there's still a value of x3 that we can print, which is 7. So our first print of x3 is 7, and our second print of x3 is 7. And so that's what happens in that case. And in our final example, what if we try a similar example to f3, except that we do not declare that the variable is local? What will happen then? So in this case, what's happening is we have a local variable named x4 that gets assigned to 7, and we print out that value when we call f4, so we print out a 7. But then when that f4 is done, this information goes away. We no longer have that x4, and so this x4, which is the global x4, is undefined. So this is something that will give us a so-called name error, or an undefined variable error, because there is no global x4. And so that's what happens in that case. This says x3 not defined. That should be, in fact, x4. The ability to declare a variable global within a function is incredibly important for any function that maintains state. So here's an example of such a function. Here we have a count function, and the first time what count returns is it returns the number of times it's been called. So the very first time we call it, count returns 1, the second time returns 2, third time returns 3, fourth time returns 4, and so on. How can we possibly implement such a function? Well, here's a simple implementation. Let's assume we have a global variable named c that's initially 0. And then every time we call count, we are declaring that any assignment is going to actually change that global variable c. So initially, c is a global variable. That's 0. This is global. And now, what do we do in the count function? We figure out what c plus 1 is, which in this case is 1, and we change c. So it changes c, so now that becomes 1, and we return that, so we get the 1. And the next time that we call c, we are going to calculate c plus 1, which in this case is 2, and change the value of c to be 2, and return that. And so what we are doing is we are changing this global value every time, and that's possible because we have declared this thing to be global. Now, what would happen if we in fact eliminated this global declaration? Let's suppose that global declaration was not there. In that case, then within this count function itself, there would be a separate variable called c. And what we would be doing is we haven't yet assigned anything to c, and yet we're trying to get the value of c when it hasn't been assigned, and we get an error that says there's an unassigned value c, because we don't know what is in this spot here. So in fact, without the global declaration, this would lead to an unassigned variable error. So the global declaration is essential for writing functions that can change some global state information. Now finally, we're in a position where we can talk about a high-low game. So here's the way we're going to play our high-low game. We're going to assume that some process has set some internal secret to a number between 1 and 100. And we have a guess function that indicates our guess at the number, and it will print out a value, rather it will print out a string that indicates whether our guess is too high, too low, or just right. So for example, let's suppose we start off by guessing the midpoint between 1 and 100, which is 50. So let's say we guess a 50, and it turns out that that guess is high. So that means that the number must in fact be between 1 and 49. So a good strategy is to then split that difference and guess halfway in between. So let's guess a 25. It turns out that that number is low in this case. Now let's guess a number halfway between 25 and 37, which, 25 and 50, which is 37. If that turns out to be high, then we guess a number halfway between 25 and 37, which is 31. If it turns out that that's high, let's guess a number halfway between 25 and 31, which is 28, and in this case it turns out that that's the secret, and we in fact have won the game. Now what we want to do is we want to start a new game by resetting the internal secret state. So we are going to call the new game function, and that's going to reset the secret to a new value. So in fact, if we now call guess a 50, maybe this time around it turns out that the number is actually greater than 50, and so our number is too low, and then we go on continue to play from there. That's how this game looks. Now what we would like to do is we would like to implement this game. And actually, I'm not going to implement it. You are going to implement it. So here's how it's going to start. You have seen before in your problem set 2 the random module, and you know that random.randint returns a number between the two values inclusive. So this is going to give you back a number between 1 and 100 inclusive, and assign it to this global variable secret. Now the goal is to go off and implement two functions. Our first function is the guess function. The guess function is going to take a number n and either print out high, low, or you got the secret. And it does so by comparing it to the secret number. And the second thing we want to implement is the function newGame. newGame takes 0 arguments. But what it does is it's going to go off and going to change the secret number by calling random.randint again. I am not going to come back and show you solutions, but you can find the solutions by going into the lecture 5 code sols.py file and see in fact how these work. So what you should do right now is you should go into the lecture 5 code.py file, which has skeletons for these guess and newGame functions. You should try to implement them, and then you should test them to see if they work. And of course, HighLow is only one of the many different kinds of games that you can build with conditionals. On your problem set 3, you're going to be implementing a rock, paper, scissors game, and there are many other games that you'll be, and other examples using conditionals that you will be implementing throughout the semester. And thus endeth the lecture slides on Booleans and conditionals.